Good morning, everyone. Let us begin today's class with an understanding of three-phase AC supply, three-phase AC circuits to begin with. Okay, so in the previous video, I have already done regarding certain concepts related to three-phase AC circuits, which are generation of three-phase power, advantages of three-phase power over single phase. In this video, we are going to discuss regarding three-phase balanced three-phase balanced circuits, three-phase balanced AC circuits to be precise, three-phase balanced AC circuits. So now, when I talk about the term three-phase, so it is called as a three-phase balanced system also, three-phase balanced system. Now, when I talk about this three-phase balanced AC system, I have to call it as a three-phase balanced system only when the magnitude and frequency are same. Magnitude and frequency, magnitude and frequency are same. Okay, next one, I'll be having this 120 degree electrical degrees, 120 electrical degrees to be the phase difference, to be the phase difference between all the three phases, between all the three phases. Okay, next you have the phase sequence, particular phase sequence to be followed, particular phase sequence to be followed, particular phase sequence to be followed. Okay, so when I say magnitude and frequency are the same and you have 120-degree displacement, that is the phase difference between all the three phases, and the phase sequence is to be followed. Now the magnitude and frequency, once when I talk about the magnitude and frequency, it is both a line voltage and phase voltage, both line voltage and phase voltage. Next, both line current and phase current, both line current and phase current. Okay, so this is what do you mean by the magnitude of the three phase balanced AC circuits once I call it to be the same. Okay, so once I have these line voltage and line current, phase voltage and phase current, as we talk more about three phase AC circuits in the coming classes, so we'll be highlighting more on the definition part of it in the later part of the video, and how to solve certain numerical problems based on a given line voltage, given phase voltage. So when to take line voltage, when to take phase voltage, and so on. So we are going to discuss in detail once we come with the definition of it. Next, we have the derivation part, and next we are going to solve it in the numerical problems. So all those things will be covered in depth. Okay. So now what I'm saying here is the frequency. I know that the frequency would remain the same. That is not a problem. Okay. Next, we have 120-degree phase displacement. Okay. So 120-degree phase displacement is one thing, and you will be having R phase. Okay. And you have Y phase like this, and you have B phase like this. Okay. So R, Y, and B. Okay. This one is the red, this one is the yellow, and this one is blue. So I have 120-degree phase displacement with respect to each other. So that is 120 degree. Okay. So now you can see that if I take R as a reference and Y is lagging by an angle of 120 degree and B is lagging by an angle of 240 degree with respect to R. So, but between the phases, okay, between the phases, I repeat the word, between all the three phases, there is 120-degree phase displacement. Okay, so 120 degree as the phase difference, the angle, that is the electrical degrees which is there, that is said to be 120 degrees as the phase difference. Okay, now next I have the phase sequence to be followed. So once I have this phase sequence, that is R, Y, and B. Okay, now this will have one direction of rotation, DOR, which is the direction of rotation. So now if I want to follow another direction of rotation, okay, so if this direction of rotation to be counterclockwise direction, and if I change any of the phases, if I interchange any of the two phases, okay, so interchange any two phases, interchange any two phases, I can change the direction of rotation to be clockwise rotation. Okay, so if I change, so what did I do here? From RYB, I interchanged it to RBY or any two phases. So it might be YRB also. So that would have the change in the direction of the rotation. Okay, so DOR refers to direction of rotation. DOR refers to direction of rotation. Okay, so DOR refers to direction of rotation there. Okay, so these are the points that we need to keep in mind. Okay, keep in mind to say it to be a balanced system, a three-phase balanced AC circuit. Okay, so these are the points that we need to keep in mind, and always we have to understand all the numerical problems and the derivation part. Okay, what we are going to discuss, so that will be for a three-phase balanced AC circuit. So it is said to be balanced AC circuit always. Okay, so these are the 3 points. So point number 1, point number 2, and point number 3. So all these 3 points have to be the same. Fine. Moving on to the next one, I have types of connections in three-phase system. Types of connections in a three-phase system. Okay, in a three-phase system, in a three-phase AC system, okay, so there are two types of connections. There are two types of connections. One, which is star or Y. Okay, next one we have delta or mesh. Okay, delta or mesh. So this one is the delta symbol, and this one is the star symbol. Okay, so now in a three-phase AC system, once we call it to be a star connected, okay, so once we call it to be a star connected, so we have the 3 windings. Let me take the example of 3 windings. Okay, so let me take the first winding as R, what I've written here. This one is R, this one is Y, and this one is B. So this one is R1, R2. Next, this one is Y1, Y2. This one is B1. This one is B2. Okay, now in a star connected network, in a three-phase star connected balanced network, okay, so now either the starting ends or the finishing ends are joined together to form a common point, which is called as the neutral connection. Okay, so either the starting ends, either the starting or finishing ends, are connected to a common single point, So these connections are called as, or these type of connections is called as star or Y connections. Star or Y. Okay, star or Y connections. Okay, so either the starting ends are connected. Okay, so either the starting ends are joined together to one single common point. So this is termed to be this common point. This common single point is termed to be the neutral point. Okay, so let me erase this here. Yes, so this common point is called as neutral. Okay, either the starting ends or the finishing ends. So this is the finishing end, whatever I have drawn here. Say R1, comma R2 and R3. Similarly, R2, sorry, 1 minute, R1, okay, next Y1, next B1 and B1, okay, next R2, Y2 and B2. Okay, now these things are to be the starting ends, starting end. Okay, so this is said to be the finishing ends. Okay, so now either the starting end or the finishing end are connected to one single common point, so that point is called as neutral point. The common point, the common point n, okay, is called as neutral point. Neutral point, okay, we call it as n. Fine. So now, in case of the neutral which is present there in the system, okay, so we can have the circuit level representation of a star connection. So this is how I can generally interpret based on the definition of star connection. Okay, so now I have this neutral point which is there, which is used for grounding purpose. Okay, I'll tell you later. So now how this is being represented in terms of the circuit. So this one is one of the conductors, this one is another conductor, okay, this one is another conductor. Okay, now I have R, Y and B. Okay, now this one is R1, this one is R2. I already told you this is a star connected network. If I have Y, this would be Y1, this would be Y2, and this would be B1, and this would be B2, and this is the common point here. So now this is the common point which is called as N. Okay, so these are the terminals of the three-phase system which are there. Okay, so now this is a star connected system. Star connected system. Star connected system. And this is the neutral wire which is used for the grounding. This is the neutral wire. This is the neutral wire. Okay, so now I have this neutral wire being present. Okay, so how many wires you can see here? So we have this star connected network to be three-phase 4-wire system. Three-phase 4-wire system. Three-phase 4-wire system, or we call it as star, star, or Y connection. Star or Y connection. Star or Y connection. Okay, so we have presence of neutral. Okay, so one thing we can see here, we will be having presence of neutral in a star connected system. Presence of neutral in star connected system. Star connected system. Okay, so now I'll tell you the definition of certain common terminologies that we are going to use. Okay, so we have certain common terminologies what we can use it. Okay, so in case of three-phase networks or three-phase system or three-phase AC circuits which are there. Okay, so let us discuss more about the common terminologies to be discussed. Okay, so let me write here common terminologies. In a three-phase AC circuits. In three-phase common terminologies in a three-phase AC circuits. Okay, so the first point being, what is the first point? So I have line voltage. The line voltage. line voltage, we call it as EL, or we call it as VL. Okay, now how do you define line voltage? So the voltage or the potential difference, the voltage or the potential difference between any two lines, between any two lines in a between any two lines in a three-phase AC circuits. In a three-phase AC circuits is called as line voltage. Is called as line voltage. So it is EL or VL. EL or VL. Okay. So now, how do I represent the line voltage is, or in terms of definition, the voltage or potential difference between any two lines in a three-phase AC circuits. Okay, three-phase AC circuit is called as the line voltage, which is EL or VL. Okay. So now, for example, okay, so how do I write it in case of this one? Okay, so how do I write it in case of the system over here? Okay, 1 minute. Yeah, 1 minute. I think I have a problem. Okay, so sorry for the disturbance, and you can see here. So now, how do you represent it? A line voltage here. Okay, so now this is R phase, and this is Y phase, and this is B phase. So if you measure the voltage across any two lines, okay, so I have a voltmeter. Okay, I have a voltmeter. So if I measure the voltage across these points, AC voltmeter. Okay, so now this voltmeter will have a range of 0 to 600 volt, because the three phase voltage level will be 415 volt, and will be having 10 amperes to 15 amperes of current. Okay, so 415 volt in the market will be having 0 to 600 volt AC voltmeter. Okay, so now I have 0 to 600 voltmeter. So if a voltmeter is used to measure the voltage across any two lines, so that voltage will be termed as the line voltage. For example, you will be calling this as ERY, or we can call it as VRY. Okay, ERY or VRY. Okay, so I can call this, for example, so VRY will be equal to minus VYR. Okay, so VRY would be equal to minus VYR, because if it reads a value, positive value, and if I interchange the connection, so if it would definitely read a negative value. Okay, so VRY would be equal to minus VYR. Okay, so VRY equals my VYR, okay, in the negative sign, and next we have VYB, and next we have VBR. Okay, so depending on the connections on how you make it, okay, so how you make it, you will come to know that these subscripts, okay, double subscript notation, whatever I have used here, which is termed as the line voltage. Okay, so VRY, VYB, and VBR. Okay, so all these things are said to be the line voltages, and VBR are said to be the line voltages. The line voltages. Okay, so these are said to be the line voltages, which is VL or EL. Okay, so VL or EL. Okay, so now if I measure the voltage between any two lines, so whatever the reading that you get, okay, so that is termed as the line voltage. Okay, that is termed as the line voltage. So now in this figure itself, okay, so I'll be calling, yeah, let me write it here as EL, or I'll be calling it as VL. So this voltage, whatever that is there, it is called as EPH or we call it as VPH. Okay, EPH, or we call it as VPH. So that is termed as the phase voltage. So along with any of the lines in a three-phase AC circuits, balanced AC circuits, if I measure it to the neutral, okay, if I measure it to the neutral, so if I have an voltmeter like this, so if I connect another voltmeter, okay, so which is of the rating 0 to 300 volt, okay, so if I connect to any one of the lines in the neutral, that will be termed as the phase voltage. That will be termed as the phase voltage. Okay, so I'll tell you the definition of phase voltage right now. So for example, let me write down here VRY, next VYB and VBR are said to be the line voltages. Are said to be the line voltages. Are said to be the line voltages. Okay, are said to be the line voltages. Okay, so now these are the double subscript notation that we are going to use it. Double subscript notation. Double subscript notation that we are going to use. So go through the textbook once. You will be having this double subscript notation because to measure the potential difference, you need two terminals. That's the reason why we will be having this double subscript notation. Okay, next one, point number 2 is phase voltage. Point number 2 is phase voltage, that is EPH or VPH. Okay, EPH or VPH. So let me write down here the voltage or potential difference. The voltage or potential difference. The voltage or potential difference between any one of the lines, any one of the lines and the neutral conductor and the neutral conductor in a three-phase AC circuit. In a three-phase AC circuit, is called as phase voltage. Is called as phase voltage, which is EPH or VPH. It's called as EPH or VPH. Okay, so that is what you term as the phase voltage. So the voltage or potential difference between any of the lines and the neutral conductor, in a three-phase AC circuit is called as the phase voltage, or the potential difference across any one phase. The potential difference across any one phase is termed as the phase voltage. So one phase is there. So if I measure the voltage across any one phase, it is also called as the phase voltage. Okay. Now, here you are going to have VRN, next similarly VYN, okay, VRN, next VYN, okay, next VBN, okay. So all these three voltages are said to be the phase voltages, EPH or VPH. Okay, so EPH, or we call it as VPH. Okay, so that is what you term as the phase voltage. So that is what you term as the phase voltage. Okay, so for example, I have VRN, okay, VYN and VBN are said to be the phase voltage. Are said to be the phase voltage. Phase voltage. Okay, phase voltage. Okay, so these two are with respect to the voltage here, line voltage and the phase voltage. Next, we have line current and phase current. Third one, line current. Line current. Okay, so line current, which is IL. So fourth one, we have phase current. Phase current, that is IPH or IP. Okay, so IPH or IP. So line current is what do you mean by the current flowing, the current flowing through any of the lines, in a three-phase AC balanced circuits, three-phase AC balanced circuits is called as line current, is called as line currents, line currents. Okay, so we call it as IR, IR. Next we have IY, and we call it as IB. Okay, so we have IR, IY, and IB, which is there. Okay, so that is where we are going to call it as the line current. So let me come back to the diagram here. Here I have IR, this is IY, the current. This one is IB. So from the network, from the three-phase network, I'll be having the current which is being flowing towards the load. So this would be the three-phase AC circuits which acts as a supply. Okay. Now the same thing once we have the phase current. Okay. So the current flowing through, the current flowing through any of the phases, any of the phases in a three-phase balanced AC circuits. The three-phase AC balanced circuits is called as phase currents. Yes, phase currents. Okay. So similarly, in a star connected network, we have both line current and the phase current to be the same. Okay. So both will have the same value. Okay. But in delta connection, we are going to have different values based on the derivation what we are going to do now. Okay. So I'm just giving you a highlight of the certain terminologies that we are going to use. Along with that, we are going to have the power consumption in a three-phase AC circuit also. We'll discuss in detail as we proceed. Okay, so the next topic what we are going to discuss is voltage and current relations. Voltage and current relations. Voltage and current relations in a three-phase AC circuits. In a three-phase AC circuit. So voltage and current relations in a three-phase AC circuits. So first one, that is the star connection. First one, that is the star connection. Okay, so I'm just going to give you the diagram here of a star connection. Okay, so we're going to have Y, we're going to have B. So this one is the neutral conductor which is there. This one is neutral, this point is neutral, and this is R1, R2. Next we have Y1, Y2. Next we have B2, this one is B1. Okay, so finishing ends of all the conductors are connected to one single point, and that point is called as the neutral point. So this is N. Okay, this one is called as N. So now if I measure the voltage across any two lines, so that would be the line voltage. So this is a star connection. This one is a star. Okay, so we call this star connection to be a three-phase four-wire system. A three-phase four-wire system. Three-phase four-wire system. Three-phase four-wire system. Okay, so now I have this line voltage. Okay, so now just before writing the line voltage, I need to draw the vector diagram. I need to draw the vector diagram. Okay, so this vector diagram, what I'm going to write now is having the RMS value of the phase voltage. Okay, RMS value of the phase voltage. RMS value of the phase voltage. Okay, so this we are going to have the RMS value of the phase voltage. So whatever that we are reading here is RMS values. Okay, so vector diagram is drawn with respect to RMS value of the phase voltage. Okay, so this one I can call it as ER or VR. Next we have EY. Next we have EB. This one is EY. This one is EB. Okay. Now similarly, I have 120-degree phase displacement with respect to each other. As I already told you, it's a balanced three-phase AC circuits that we are solving in this module. Okay. Now, if I trace it back, I'll be having minus ER. This one would be minus EB. This one would be minus EY. Okay, so this one is a vector diagram what I have written here. So let me move on to the derivations what we are going to have. So let us consider a three-phase AC circuit. Let us consider a three-phase AC circuit, okay, where ERY, EYB and EBR are said to be the line voltages. And ER, EY, ERN, next EYN and EBN are said to be the phase voltages. Okay, now I have drawn the vector diagram there. Okay, so it's for a three-phase balanced AC circuit. Okay, so always remember we are going to draw it with respect to three-phase balanced AC circuit. So in star connection. Okay, so I have ERY and as the line voltage and ERN, EYN and EBN to be the phase voltage there. Okay, so now from the vector diagram, I have ERY which will be equal to ER minus EY, okay, which is the vector difference. I can also write it in terms of vector sum. ERY would be equal to ER plus of minus EY, which is vector sum. All right. So now I have both vector difference and vector sum. Let me come back to this vector diagram. So I have traced it back. The magnitude would remain the same, and there is only change in the sign, if you can observe clearly. So what is the angle between EY and ER is 60 degree. Now I trace it at the midpoint, okay, which will give me ERY, okay, okay, it's a parallelogram. So this angle would be 30 degree. Okay, now if I have EYB, okay, so this would be the thing. Okay, next if I have EBR, so this one would be the angle. Okay, so this one would be the angle. So this would be the resultant and all. So I'm just showing you for one of the phase and the line voltage, which is ERY and ER. Okay, so I want to establish a relationship between the line voltage and the phase voltage here. Okay, so now if I have the line voltage and the phase voltage, so this one is the line voltage, and these two are the phase voltages. Okay, so now from vector diagram it is clear that we have both vector difference and vector sum. Fine. So now if you recall the law of parallelogram of forces, you will have the resultant, which is ERY, which will be written as root of ER squared plus EY with a negative sign squared plus 2. I'll take only the magnitude, that is ER and EY. So I have next one, which is, yeah. So I need to find out the angle between ER and EY. So what is the angle between ER and EY? So that is 60 degree. That is 60 degree. Okay. So cos 60 degree. So cos phi. Okay. So cos phi value, whatever that is there. So that is the angle between ER and minus EY. Angle between ER and minus EY. Okay, so angle between ER and minus EY. Okay, so we have, let me solve it quickly. ER squared plus EY squared plus 2 ER EY. Okay, I'll take out the magnitude, hence we are taking only the magnitude. Okay, so that is ER into EY. So cos 60. Okay, so cos 60, what we are going to have? Okay, so that sine 30, that would be equal to 1 by 2. So this value cos 60 degree, that would be equal to 1 divided by 2. Okay, so now I have root of ER squared plus EY squared plus ER into EY. Okay, ER into EY. So for a three-phase balanced AC circuits, for a three-phase balanced AC circuits, okay, so we have ERY equals EYB equals EBR. So that would be equal to EL or VL, which is the line voltage. Which is the line voltage. So next, similarly, we are going to have ERN, okay, or ER or ERN. Okay, that would be equal to EY. Okay, so we can write it as ERN or EY, which remains the same. Okay, EY, which will be equal to EB. So that will be equal to EPH or VPH or VP if you want to write it. It is fine. So that would be the phase voltage. So you have line voltage and the phase voltage here. Okay. So after writing it, I have EL, that would be equal to root of, okay, root of EPH squared plus EPH squared plus EPH squared. Okay. So it would be written as root 3 into EPH. Okay. So how did I write it? So this is from the simple math rule. Okay, so I have the line voltage. Okay, that is the line voltage will be equal to root 3 times the phase voltage. Root 3 times into the phase voltage. Okay, line voltage will be equal to root 3 times the phase voltage. Okay, so now relation between line current and phase current. Relation between line current and phase current. So this was the relation with respect to line voltage and phase voltage. So now the line current and phase current. Okay, so I have IL would be equal to IPH in a star connection. In a star, okay, I'm write the symbol. In a star connection, line current equals phase current. Line current equals phase current. Line current will be equal to phase current. Okay, so that is how you can have the derivation being done. So now I have the line voltage and the phase voltage relationship, and I have the line current and the phase current relationship. Okay, so in a star connected system, each outgoing line is connected to a separate phase. The current flowing through the lines and the phases are said to be equal. Okay, now the power equation. The power equation. I have the power output per phase, the power output in each phase. Okay, let me talk first as each phase, which is nothing but power output per phase. Power output per phase. Power output per phase. Okay, so now I have the phase difference between respect to the phase voltage and the phase current. Yeah, the phase difference, the phase difference of phi will be with respect to the phase voltage and phase current, phase voltage and phase current, phase voltage and phase current. Okay, I have the angle to be phi. Okay, so that is P will be equal to, I have the phase voltage as VPH or VP, and I have phase current as IP, and I have cos phi as the power factor. P will be equal to VPH into IPH into cos phi. Okay, now in all the three phases, in all the three phases, in all the three phases we have, in all the three phases we have power in all the three phases is given by 3 times Vp into Ip into cos phi, Vp into Ip into cos phi. Okay, now to represent in line voltage and line current, to represent the power in all the three phases, the power in all the three phases, which is total power, okay, so which is P will be equal to 3 into VPH into IPH into cos phi. We have VL to be equal to root 3 into VP, and I have VP that will be equal to VL divided by root 3. Okay, so that is 3 into VL divided by root 3 and IL into cos phi. Okay, so now I have that is root 3 VL IL into cos phi. So P will be equal to root 3 into VL IL into cos phi, or we can write it as in terms of the phase voltage, that would be 3 into Vp into Ip into cos phi. 3 into Vp into Ip into cos phi. Okay, so now you might get the derivation, either the star connection or the delta connection. You have to write the circuit diagram, you have to write the explanation and write the vector diagram which is there, and show the relation of vector difference and vector sum. Next we want to list down the relation between line voltage and the phase voltage. Okay, so next we have the power output equation. So this is the relation between line voltage and phase voltage and line current and phase current in a star connected network or a star connected AC circuits. Now I have the power equation that is for one single phase. So this one is for one single phase that we have. Next for three phases, that is 3 into Vp into Ip into cos phi. Next we have the representation of the line voltage. So in terms of line voltage and line current, in terms of line voltage and line current, in terms of line voltage and line current. Okay, so power in all the three phases, okay, so this is a small derivation that we have. So this question might be asked in few other ways also, then it would be easy for you to remember how a question will be asked in the test or an examination. So you can make it quite simple. I'll tell you how to approach or how the question will be there for such derivations once I finish with delta connection also. Okay, so we will stop here, and the recorded video will be shared. Okay.